Hey mathematicians, let's quickly do the example they offer in 1.1 and give you a quick taste for differential equations doing a well-known or a familiar topic. Apples falling from trees. I always sing apples falling from trees. Maybe not, but we'll pretend. I'm going to cover my apple blue, and we are going to say that this apple is falling a distance h. Okay, and so maybe the question is, where is this apple at any given time t? Right? So that's the question. And so what do we know? Well, being the physicists that we are, we know that F equals ma, right? I also know that in this situation for A, I'm talking about G, right? Particularly, I'm talking about negative G because I'm falling down. So I'm going to define falling down as negative, or going downward is negative, going upward is positive, equivalent with the coordinate system. So we're going to make this a negative mg on the left-hand side. And then on the right-hand, or excuse me, on the right-hand side, know your left from right, Beth. So on the right-hand side, I'm going to change that to negative mg. On the left-hand side, I'm going to go ahead and replace this f with m d squared h dt. Okay? Why? Because I know that acceleration equals the second derivative of distance, right? Velocity equals the first derivative. Acceleration equals the second. You guys probably know that from calculus. Now let's go ahead and solve this Diffy I know it's a Diffy because it has a derivative. It has a second order derivative. Okay? But this one's quite easy to solve, so we can do it. So just like when we solved equations in algebra, we're going to do the same thing to both sides of the equal sign. What do I do to one side of the equal sign? I have to do to the other. And it seems like a really good idea right now to, one, cancel out these m's, and then two, let's integrate both sides with respect to t. Oh, I forgot my integral. There we go. Okay, and so what is the integral of the derivative? It's just the function itself, so this is going to reduce this by 1. And then over here, we're going to end up with gt plus c, right? We're going to go ahead and do this again. Make sure we take the derivative of the whole entire left and right. Make sure I put my dt's. I'm very bad about things like this, little mini details. I'm kind of a, oh yeah, that's good enough, that's close enough kind of person. But it's important that we know what we're integrating in relationship to, right? You're asking yourself what's on the x-axis. That's what you're asking when you stick this little guy in. And so again, the integral of derivative is just the function itself. And so this time on the left-hand side, we end up with that function in terms of t. And it's going to equal negative 1/2 gt squared plus c1t. I've named this c1 because now I've got another guy, c2. Okay, hold on. I'm going to do an intermediate step that I skipped because I'm like that. So this is going to end up with, yeah, no, I'm going to do it like that. So you would split this up, yeah? And so what would that give you? That would give you your negative 1/2 gt squared plus some c, right? Plus, and then the integral here would give you c, I'm going to call it c1, yeah, what am I going to call it? I'll call it c2. c2t plus a c3, right? So this is the constant you get here, right? And then I integrate this constant, and I turned it here, I made it c2t, and then this is the constant I get here, right? So I get two constants, but a constant plus a constant is just a constant, so I just combine those, if that's what happened. If that confused you, ignore everything I said. And then this guy just comes over here. Okay, and so what does this look like? Well, I hope it looks just like this to you, right? And so this is our function that is our solution, like we said, right? So our solution is a function. It's a family of curves, right? And then once I know my initial conditions, I can find the unique solution or the single solution to this, okay? And so this is just 1.1, the example they give, just to give you a little taste of what we're going to do this semester.